Hi friends, in this video we're gonna solve a problem on Butterworth filter. So whenever we see the response of a Butterworth filter, this is the response of the Butterworth filter. Okay, and this will be my stop band attenuation. This will be my pass band attenuation. This is 1. This is maximum. Omega p. Yes. Okay. So this is my frequency response of a Butterworth filter. Okay. And here they have given that 3 dB attenuation at 500 Hz and 40 dB attenuation at 1000 Hz. Design the filter. So whenever they ask us to design a filter, the two important parameters we require to design a filter is, one is order. The second most important parameter is cutoff frequency. Okay. One is order. Second is cutoff frequency. Okay. Now we'll write the given data in an appropriate form for easy understanding. They are given 3 dB attenuation at 500 Hz. First we need to see, or we need to classify the given question into pass band and stop band frequencies and attenuations. They have given 3 dB attenuation at 500 Hz. We know that in pass band my attenuation is alpha p, and that is much lesser than compared to the attenuation of stop band. Why? Because now whenever you consider this part, okay, and this is in this way, the deviation from the ideal characteristic of the Butterworth filter, this maximally flat response is given by my pass band attenuation, right? So if this is 1, this will be a 0.7 or 0.8 or 0.9 in the same values, like 0.1 increment values approximately. So this difference gives my attenuation. Okay, so I am taking here my alpha p to be 3 dB frequency, 3 dB attenuation. So whenever alpha p is 3 dB attenuation, then definitely my pass band frequency will be 500 Hz, right? My pass band frequency will be 500 Hz. 40 dB attenuation is 1000 Hz. In this value, in stop band, we have much difference between the ideal characteristics and the practical characteristics. So I will take alpha s to be 40 dB. Whenever it is alpha s, then it will be fs, right? This is 1000 Hz. But here we deal with the radians per second frequencies, that means angular frequencies. So I need to convert this to omega p by multiplying it with 2 pi. This will be 1000 radian per second. Similarly, this will be 2000 pi radian per second. Okay, now we need to calculate the order. I hope these are the sufficient terms I require for calculating the order. For a Butterworth filter, order is given by n greater than or equal to log of under root 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 whole by log of omega s by omega p. Okay, this is my order, the order formula for Butterworth filter. Okay, I think I have alpha s, I have alpha p value, I have omega s value, and I have omega p value. Directly substitute there. This will be 0.1 into alpha s is 40, so this will be 10 power 4 minus 1 by 0.1 into alpha p is 3, so 0.3 minus 1 by, this is omega s by omega p. Omega s is 2000 pi, this is 1000 pi, so directly I can write this as log 2. Okay, after solving this I will get approximate value as 6.67. 6.67. So as I need to round it off to the nearest higher integer, I will take my value as 7. Okay, this is my order of a Butterworth, given Butterworth filter. Next is finding the cutoff frequency. Okay, before that, if they asked us to find the order of this filter and also find the poles of this filter, where the poles location of this filter, then how we need to do is that we have a formula, okay, directly for calculating the poles, right? That is given by Sk is equal to omega c e power j 5k. Sk is equal to omega c e power j 5k. Till now we did not require omega c value. Okay, we did not find out omega c value, but if they did not mention the omega c value as 1 radian per second, that is normalized one, we need to calculate the omega c value also. Okay, omega c value also need to be calculated. Now I got my order as 7. So I need to calculate the poles location. Here in this equation I have two unknowns. One is omega c, one is 5k. So for a Butterworth filter, I get my 5k values as pi by 2 plus 2k minus 1 pi by 2n. Pi by 2 plus 2 pi 2k minus 1 into pi by 2n, where here n is order, that is 7, and k value runs from 1, 2, 1, 5, 6, 7. K value runs from 1 to n, that is 1 to 7. As if I substitute these values here, I get my values of 5k, and if I substitute e power j 5k value here, I will get my poles. And I need to know even omega c value also. Omega c value can be known if we know either omega p value or omega s value, okay, as omega c value is known by omega p by 10 power 0.1 alpha p minus 1 whole power by 2n. If I know only passband frequency and passband attenuation, that is enough for me to solve for cutoff frequency. Or else, if I know stop band frequency and stop band attenuation, even that is sufficient for me to calculate my omega c value. So from here I get omega c value, cutoff frequency, and from here I get my 5k value. So directly I will substitute my values here, omega c e power j 5k. Okay, now let's do it for, I'll do it for n equal to, k equal to 1, n equal to 7 and k equal to 1 to 3 values, and I'll find out what is my, what will be my poles location. Okay, so now from here you can calculate the omega c value directly. Here no unknowns are there, n is already known, it is 7. My alpha p is known, Alpha omega p is also known. Directly substitute here, you get the cutoff frequency value. So for finding out this, suppose phi 1, that is pi by 2 plus 1 by 2 into 7 into pi, that is pi by 2 plus pi by 14. This is 8 pi by 14, which is 4 pi by 7. This is my phi 1 value. Similarly, phi 2 value will be pi by 2 plus 3 pi by 14, that is 10 pi by 14, that is 5 pi by 7. Next will be here, I got 1, 3. Next will be here again 5 and 7 plus 5. This will be 12 pi by 14, that is 6 pi by 7. This will be my phi 3 value. Next will be what? 8, 10, 12 and 5 is over 7. 7 plus 7, 14 pi by 14. I'll get 4 value as pi. Okay. So I'll get 4 multiples of pi by 7 here. Like 4 pi by 7, 5 pi by 7, 6 pi by 7 and pi, 7 pi by 7, 8 pi by 7, 9 pi by 7. Like that I get 7 values. I'll substitute in this here and I'll find out my omega c so that I'll get my locations of poles. This is how we solve for the design of the Butterworth filter when passband attenuation and stopband attenuation and passband frequencies and stopband frequencies are given. That's all for this video. In the next video we'll see how to calculate the poles location for a Chebyshev filter. Thank you.